A quick recap of the concepts of game theory that we have learned before we learn a couple of new things. And because I know that this might be a question that you might wonder about, we're going to basically learn the concepts that you need to finish homework 5, and everything we teach today and you solve on homework 5 is fair game for me too. Okay? Homework 4 is due on 14th, which is tomorrow. So let's start with a recap of game theory. What we said about game theory is that this is the systematic study of strategic interactions. Strategic interactions means that these are situations where the outcome depends not only on what you do, but also what others do. And we started with talking about many examples, and this is an example that we solved in the class, in the last class. And I want to start by just talking about this example to begin with. So this was an example where there are two firms, United Airlines and American Airlines. They're trying to decide how many thousands of passengers to fly each quarter, which is what you see as their actions. Remember, to describe a game, I need three things. I need to tell you who the players are, and here the players are going to be United Airlines and American Airlines. I need to tell you what their actions are. The actions are how many thousands of passengers they fly every quarter. So that's 64 or 48,000 passengers. And I also need to tell you what the payoffs are for each possible action that each of the players can take. And those payoffs are described by the table. When you read the table, it tells you what payoffs arise at the intersection of each possible action. So those are the three pieces of information you really need to describe a strategic scenario in the form of a game. And that's what we have. The next thing that we talked about, and this is just part of the review again, is we said that, look, whenever you find a game, you want to figure out the best responses for each player. That's probably the first thing you want to do. So best responses for each player. So let's just do that right now. Let's say that we're going to use triangles for the best responses of United Airlines, and we're going to use squares to denote the best responses for American Airlines. That's going to be our notation. So let's start with the first question. So let's say that you know that American Airlines is going to fly 64,000 passengers, so they're going to place 64. I want you to tell me what do you think is going to be the best response for United Airlines. Okay? Is the question clear? So anyone, what would be the best response for United Airlines? Go ahead. Tell us which numbers you compared to get to your answer. Very nice. So if you know that American Airlines, if AA plays 64, then as United Airlines you can either play 64 or 48 against it. They would respectively give you payoffs of 4.1 or 3.8. 4.1 is better, which means that the best response for you would be to try and get this 4.1 by playing 64. Then if American Airlines plays 64, your best response is also to play 64. Very nice. Let's go to the next part of it. Suppose American Airlines instead was playing 48. What would be your best response then? Go ahead. Also 64. What are the numbers you compared to give us the answer? 5.1 and 4.6. We compared 5.1 and 4.6. 5.1 is better, which tells me that United Airlines' best response is also to play 64, which is why I'm going to put this triangle next to that action. So 64, United Airlines' best response is to always play 64. That's what it turns out to be. Now let's think about American Airlines' best responses. So let me use a different ink. So this is going to be AA's best response. Let's think about it quickly. If United Airlines plays 64, let's think about what American Airlines should do. So this is United Airlines playing 64. Someone else? Could you tell me? Go ahead. Tell us what numbers you compared.
I compared 4.1 and 2.8.
So you would compare this 4.1 to this 3.8. These are the two things that you can do as American Airlines against 64. 4.1 is the better thing to do than 3.8. So the best thing you can do is, the best response is to place 64. And this means that I'm going to put this square to denote that this is the best response for you as American Airlines. Very nice. That brings us to the last possible case. And this is when American Airlines is playing against United Airlines playing 48. Someone else? What would be the best response here? Go ahead.
64.
Yes, which numbers do we compare?
5.1 and 4.6.
Very nice. I would compare this 5.1 to the 4.6. 5.1 is better. So it means that even if United Airlines is playing 48, you want to keep playing 64. So that means that I need to put this square over here. So the best response for American Airlines also is always to play 64. And this gives us what we call the dominant strategy last time. Right, so the way to find Nash equilibrium here was note the cell where, not where, let's make it clearer, note the cell with both triangle and square. This is this cell over here. This gives us the Nash equilibrium of the game. This gives us a Nash equilibrium. And how should we describe the Nash equilibrium? Should we say that the Nash equilibrium is 4.1, 4.1? Or should we describe it as the Nash equilibrium is UA plays 64, AA plays 64? Should we say the former or the latter? Which is the right way to say it? The latter. Okay? So the way to describe a Nash equilibrium is not to say that the Nash equilibrium is 4.1, 4.1, but instead you want to describe the actions, which means that the way to write it is UA plays 64 and AA plays 64. Even though when you see the cell, you might be tempted to say that the Nash equilibrium is 4.1, 4.1. That's not how we write it. We always write a Nash equilibrium in terms of the actions, the best responses that people are playing. So we basically want to say that the Nash equilibrium of that game is UA and AA both playing 64. Now, I want to show you a different game because it's going to lead us to learn a different concept. So the game I want you to see is this one. So, what is the situation describing? I have described it in terms of my favorite game, which is soccer, but I could have described it in terms of almost any game which has a ball. I didn't play with the ball. So I could have talked about tennis, I could have talked about basketball, soccer for sure, because most games with most games with a ball, there's an element of trying to wrong foot your opponent. If you're playing basketball, if you're dribbling, the idea is you want to act as if you're going to go one way and then quickly go the other way, so you wrong foot your opponent. If you're playing tennis, if you're playing ping pong, the idea is the same. You want to make shots where your opponent is going to have a hard time understanding where the shot is going to end up. Particularly for this game of soccer, I want to model something very simple. Soccer can be a complicated game, but I want to model this very simple thing where all I want to think about is there is a goal, there is a goalie who is standing in front of the goal. Their job is to save the goal if they can. And then there is an attacker with a ball at their feet, and the attacker has two possible actions. They can either kick the ball left or they can kick the ball right of the goal. So this is the attacker's two possible actions. And then the goalie has two possible actions. The goalie can either dive left or dive right. So I'm taking something that is actually more complicated than this. I'm just simplifying it in terms of just each player having two actions. Two players goalie and an attacker, each having two actions. And then, intuitively, as you would understand, the goalie's job is to save the goal. So, if the goalie dives in the same direction as the kick, then the goalie wins and the attacker loses. So, if the attacker kicked left and the goalie dove left, then the goalie saved the goal, so the goalie wins and the attacker loses. Similarly, if the attacker kicked right and the goalie dived right, the goalie wins and the attacker loses. And then in the other two cases, the opposite happens. The attacker wins and the goalie loses. Exactly how you would think this game is. Okay, so why is this a game? Because I have described the three things that I need to describe the game. I have described the players. The players are these two people, the goalie and the attacker. I have described the actions. I have made the actions really simple. They're basically, do you dive left or dive right? Do you kick left or kick right? So the actions are simple. And then actions. And then payoffs. I have written down simplistic payoffs that happen when the goalie and the attacker interact in terms of passing. Okay. Now the reason I'm talking about this game is because the spirit of this game, if you've ever played a game of soccer or basketball or ping pong or tennis, whatever is the game that you've played which has this similar dynamic, then you know that the spirit of the game is that you want to be unpredictable as a player. The best dribbler is someone who is very hard to predict which way they're going to dribble next. The best person taking a penalty kick is someone, not only do they have a very, very fast and accurate shot, but also it's very hard to predict if they're going to go left or go right. Similarly, the best goalie is someone who you cannot predict. If you could predict them, if you knew they are going to go left, you would just go right and score on them. So the great goalie is someone who is really unpredictable. So these are games where, just intuitively, even without knowing what game theory is, you know that this is a game where unpredictability is the nature of the game, right? Both players want to be unpredictable. And I want you to have that intuition even before we start analyzing the game. Okay, there's value in being unpredictable in these games. Very good. Now the next step we are going to do is the same step that we always do, which is to figure out the best responses. So let's figure out best responses for both players. And when we figure out best responses, we are going to use the same notation as always, the triangles and the squares. The triangles for the row player, the squares for the column. Okay, so let's think about the attacker kicking left. And I'm going to now answer the questions. I don't need to ask you, this is kind of very simple. If the attacker kicks left, the goalie's best response is to dive left, because then they would just save the goal. So I'm going to put the triangle over here. If the attacker kicks right, then the goalie's best response is to dive right. And that means I'm going to put the triangle over here. Similarly, if the goalie dives left, then the attacker's best response is going to be to kick to the other side. So dive left, attacker's best response is to kick right. And if the goalie dives right, the attacker's best response is going to be kick left. And that completes the best responses that we can write down for both of the players. Those are all the best responses. Right? So we have completed the best responses. But notice something is off or different about it, which is that, note that there is no cell where a triangle and square coexist. Right? Think about each of the cells that you can see there, and what you would realize is each cell has a triangle or a square, but there is no cell which has both a triangle and a square. And what that means is the strategy we had so far, the algorithm we had so far, doesn't exactly work here, because we would be in the business of finding a cell where a triangle and a square coexist. It just doesn't happen in this case. And that means that we need to do something else. Okay? So this is an important thing to note. And that means that we need to look beyond. And if you think about the reason we want to look beyond is, this is surprising in the sense that, remember, Nash's result, I'm just going to write down Nash here, was that every game, it doesn't matter how you write down the game, how many actions there are, and what these payoffs are. It doesn't matter. Every game must have a Nash equilibrium. That was John Nash's main result. So if every game has a Nash equilibrium, it means even this game must have a Nash equilibrium. It's just that our first method that we tried isn't giving us that value. So that's what I mean by we need to look beyond. There has to be a Nash equilibrium of this game just by Nash's famous result. It's just that the first trick that we tried doesn't work. And the trick that is going to work is the trick that we already kind of intuited towards, which is that you want to think about these players trying to be unpredictable. That is what is needed to be modeled in this game to figure out the Nash equilibrium. Okay? Now, let me try and show you how this is going to work. First, I'm going to replicate the game on this slide so that you can still see the game even though I've changed slides. So, here is my table. In black. There are two players. There's the goalie, there is the attacker. The goalie can dive left or right. I'm just going to call them left or right. And the attacker can kick left or right. Okay? So, we write down the whole thing. The attacker plays this way, and the goalie goes that way. And then here is my table. I know that the payoffs are going to be exactly this. Given I have a simple story behind the payoffs, I'm just going to fill out the table. That's my table. Just replicate it from the last slide. And the other observation that I want to make on the slide is that we want to have this element of unpredictability. That's the intuition that's going to hold everything that I'm going to say here onwards together. This unpredictability. So let's go for it, right? So I'm going to show you 3 steps that you need to perform to solve this problem. So step by step. Step 1 is going to be assume what I'm calling this unpredictable strategies for both players. Okay, that's the first thing. We need to assume that these players are being unpredictable. What does unpredictable mean? It means that sometimes a goalie is going to dive left and sometimes they're going to dive right. And we need to write that down in mathematically precise language. And here is how you would do it. You would say that goalie dives left with probability. So with probability P, the P is a placeholder, and dives right is with probability. That's a very long word. I'm going to just write W.P for those 2 words. And dives right with probability, which is the residual probability, which is 1 minus 1. Let me pause there. Okay? We want to write down unpredictable strategies for both guys. Unpredictability means that as a goalie, I'm going to sometimes go left, sometimes go right. And to be precise, I also need to have some idea in my mind of how often I'm going to go left and how often I'm going to go right. And the relative frequency of those, we're going to write it down as these probabilities. So think of the probabilities as giving you some kind of relative frequency. And right now, we don't know what this goalie's unpredictable strategy should be like, so we're using placeholders. For example, it could have been that goalie dives left 50% of the time and dives right 50% of the time when they're trying to be unpredictable. And that would mean that the values of P and 1 minus P are both 0.5, 0.5. I could also have had that the goalie dives left 99% of the time, but they go left, they go the other direction, which is right, 1% of the time. And that would mean P would be 0.99. Okay? So this is just my way of having a placeholder of how often they're going to do both actions, but they're going to be unpredictable. They're not always going to play the same action. Okay, that's what the probability is by. And WP, as I said, is width probability. It's just very long, so I'm just going to use shortcuts. Now think of the other guy. For the other guy, I also want to have an unpredictable strategy. So the attacker is going to kick left with probability. I don't know what this probability is going to be. So here is my placeholder Q, and then kicks in the other direction with the complementary probability, with whatever is left, 1 minus. So for example, this could mean if Q is 0.1, it means the attacker is going to 10% of the times they're going to go left with the shot and 90% of the time they go right. And I can model all of that with just my probabilities, P and Q. That's the goal of the probabilities, P and Q. Right? So we're going to start by assuming unpredictable strategies, that is part 1, and the way we model unpredictability is through these relative frequencies, or more precisely probabilities. Step 2 is going to be to argue that such randomizing behavior, where randomizing means choosing actions randomly, requires indifference. This is just a step. I'm just going to explain what it means. But this is conceptually the second step. So what does this mean? So here is how you should think about it. Think about the goal. I'm going to say that why would the goalie be okay with playing either left or right randomly? Because right, they are playing randomly, they are playing it sometimes this, sometimes that, with some probability. Why would the goalie be okay with doing that in the first place? And then I'm going to argue that this is only possible if they were indifferent between L and R to begin with, or in other words, if somehow L and R give equal payoffs. Okay? This might still be difficult to understand, so I want you to think of it in terms of an example that I tell you right now. I'm not going to write down the whole example, I'm going to describe it, and I'm going to name the example so you know which example to think of if you ever see these slides again, or if you take notes and see this in the notes. So think about short choice for interview example that I'm going to talk about right now. So think about me going for an interview. I'm trying to get a job at a company. This is my first job out of the university, and I really want to get that job. I really care about it. I want to make an impression at the interview. If one of my shirts was clearly the best shirt I have, I would just have worn that shirt to the interview, clearly. So when would it ever be the case that you see me, for these interviews, sometimes choosing red shirts, sometimes choosing my blue shirt, or whatever, if I have two shirts? Why would it ever be the case that I randomly choose my shirts? It's only possible if all of my shirts are equally good. If one shirt was clearly the best, I would have just worn that shirt. So randomizing between my actions, sometimes choosing this, sometimes choosing that, sometimes choosing one shirt, sometimes choosing another shirt. It must mean that somehow these shots are yielding me equal payoffs. I'm somehow indifferent between the shots. And similarly, if the goalie and the attacker are sometimes playing left, sometimes playing right, it must be there is some notion of indifference that's at play. Somehow they are indifferent. Somehow these actions are giving them equal payoffs. How is that possible? That's the next step. But that must be the case. That's the argument I want you to think about. That's step 2. So thinking about why would randomization even come to happen? Like what needs to happen for these players to randomize in the first place? And randomization by either player requires some kind of indifference among actions. That's going to give us step 3, which is operationalize the indifference conditions. What does that mean? So let me make this a bit smaller so that we can also see the matrix up here. I want you to think about so fix the goalie. Think about what we have assumed on the question, and I'm going to use that notation. Remember, the goalie dives left with probability P and dives right with probability 1 minus P. So I would like you to write down P and 1 minus P next to the goalie's actions that we have assumed. These are the probabilities with which the goalie goes left and right. And then the attacker kicks left with Q and kicks right with 1 minus Q. So I want you to write down the Q and 1 minus Q next to the attacker's actions. That's the first thing. Right? So whatever we have assumed in step 1, just write it down on the matrix so that you have the P's and the Q's in their correct, specific places. Now think of the goalie. And I want you to think about the expected utility or expected payoff payoff or utility, doesn't matter. These are actually utilities. So expected utility from left for the goalie. And I want you to compare it with the expected utility or payoff from playing right for it. Those are the two things I want you to compare. And I want you to pay attention when we calculate this because it's not that easy. So think about what happens if the goalie plays left. If the goalie plays left, then whether they get the 1 or the -1 depends on what the attacker has played. What we do know is the attacker is being unpredictable. Sometimes they're going to go left and sometimes they're going to go right. So the goalie might end up getting the 1 or the -1. It really depends on how the attacker has played on that instance. What we do know is they go left or right with probabilities Q and 1 minus Q. And what that means is that the goalie is going to enjoy a win, which is a payoff of 1 with probability Q. And they're going to maybe not enjoy but suffer a loss and this payoff of -1 with probability 1 minus Q. And the attacker has decided to go right instead. So the expected payoff or utility for the goalie when they go left has to be equal to Q times 1 plus 1 minus Q times -1. And I want to pause on that. I want you to think about what we just did. We are calculating the goalie's payoff from the action of going left. And we have said that, look, the payoff depends on what the other guy does. The other guy can do one of two things. We have assumed this Q and 1 minus Q as the relative frequency when they go left and right. And the relative frequency determines whether the goalie is going to end up winning or losing with her action of going left or right. So let's just fix the goalie playing left. If they go left, they win sometimes, they lose sometimes. These are the probabilities with which they win or lose. And these probabilities are coming from the other guy's action, the attacker's actions. Okay? Is that clear why we have Q times 1 plus 1 minus Q times -1? And is it clear that Q and 1 minus Q are the attacker's action probabilities, whether they are kicking left or kicking right. Now let's do the same, but for when the goalie is going to go right. So let's think of the goalie going right instead. If the goalie goes right, then clearly they can either get -1 or 1. So these are the two possible outcomes they can get. And let's think about when or how often would they get those outcomes. They are going to get the -1 when the attacker goes left, which happens with probability Q. And they're going to get this +1 when the attacker goes right, and that happens with probability 1 minus Q. So then the expected payoff is going to be Q times -1 plus 1 minus Q times 1. Are there any questions about the second payoff? This is an expected payoff that we calculated. I want you to think about it. I want you to think about how Q and 1 minus Q play a role. And I also want you to think about what the Q and 1 minus Q mean. This is the attacker's action and how they decide whether they are going to play one action or the other. Now, think about point 2. Step 2 or point 2 was, this randomly choosing one of these actions, which is happening for the goalie, requires indifference between actions. So it must be that the goalie is indifferent. So I'm going to write the next step down, which is the goalie must be indifferent. Where is this step coming from? The goalie is also randomizing. So she must be indifferent. And this is just using the logic from part or step 2. And if she is indifferent, it means, so that is, she must enjoy equal expected utility from both actions. And because she must enjoy equal expected utility from both actions, I have equated them. That is what gives me that equation. Right? I calculated the payoffs on both sides. They have to be equal for her to feel this indifference. So I equate them. Now, if you solve for the equation, it's just a linear equation with one unknown. It's easy to solve for. Let me just tell you what you would get and put it in a box. If you solve for it, then you're going to get Q equal to 0.5. And that is going to be the first thing that we have solved for on this question. We started with these placeholders P and Q. So our goal would be to solve for P and Q. And what I'm telling you is if you solve it, you are going to get Q equal to 0.5. And you can verify it if you want. It's very simple. It's just a linear equation. Then the next step is to do the same, but for the here we fix the goalie. Now let's fix the attacker and try to see what that would give us. So let's fix the attacker. I want to draw the table again so it's clear what's going on. So reproducing the table. Here we go. This is the goalie. And this is the attacker. Their actions are left and right. And these are the payoffs. What are we doing now? What we are basically doing is, we first fix the goalie, now fix the attacker. And I want you to think about the following, which is, find the expected utility for the attacker from kicking left, and then compare it to the expected utility We want to figure those out. Impose indifference, which would mean that those two payoffs have to be equal, and then solve for it. That's the goal. So let's think about it. What's the expected utility from kicking left? We are talking about the attacker here. So here is the attacker. If they go left, given they are the second player, their payoffs are going to be either -1 or 1. Those are the two possible payoffs. So I know that their payoffs are either -1 or it's 1. What else do I know? I had this placeholder stuff which said that the goalie was playing left or right with probabilities P and 1 minus P. I already know that. And what that tells me is that when I would calculate this expected utility, I know that by kicking left, the attacker would sometimes lose and sometimes win. And they're going to lose when the goalie goes left, which happens with probability P, and they're going to win when the goalie goes right. This is where the attacker is winning, and that happens with probability 1 minus P. So that should be the expected utility from kicking left for the attacker. Let me pause there. Is this clear? Remember, we are looking at the second payoffs because this is the second player. And remember how we are using the goalie's actions to calculate this expected utility. We are looking at what the goalie is doing and how often they are taking that action, with what probability. Similarly, we can figure out the attacker's expected utility from playing right. If they are going to kick right, again, they can either get a -1 or get, if there is a mistake in the table. Let me fix the table. This one is wrong. The table was 1 minus 1 and then -1. So once I have fixed that, now let's get back to business. Expected utility from kicking right. If you kick right as an attacker, you could either win or you could lose. And whether you win or lose depends on what the goalie is doing. Could either end up getting this 1 or the -1. Those things happen when the goalie goes left and right respectively, which happen with probability P and 1 minus P. And that would give you the expected utility from kicking right for the attack. What's the next step? The next step is, remember, we need to have the indifference condition. So the equality comes from the attacker must be indifferent for her to want to randomize among her actions. And this indifference means that the expected payoffs from the actions must be equal. That's why we have equated the payoffs. And then it's just an equation with one variable, which is P, and we can solve for it. And if you solve for it, I'll tell you what you're going to get. You're going to get P equal to 1. You can try solving it on your own, but it's really very easy. This is going to give you 0.5. So what have we got so far? We started in step 1 by saying, let's have a placeholder for how they're going to play unpredictable strategies. And the placeholders were P and Q. And if you start with a placeholder, then obviously you're setting yourself up for a path where you have to solve for that P and Q. And that's exactly what we did. We solved for Q in the last page, and we solved for P on this page. And what does it tell us once we have solved for it? So go back to step 1. Step 1 is where we define the placeholders. And then what you would write down is the Nash equilibrium for this game is the following. I'm going to write it down in a different ink. So it's going to be that goalie dives left. Remember we used width probability is W dot P. Width probability P, and we solved for P. P turns out to be 0.5. That's the magic value. So goalie dives left with probability P equal to 0.5 and dives right with probability 1 minus P. If P is 0.5, then 1 minus P is also 0.5. So I can write it down as this. And the attacker kicks instead of dives. It must be the attacker kicks left with probability Q as the placeholder. And what we have done is, on the previous slide, we solved for Q, and Q is equal to 0.5. So what we can write down is attacker kicks left with probability Q equal to 0.5 and kicks right with probability 1 minus Q, which is also 0.5. Okay, so let's take stock on what we got. We started with this problem, which I said that it describes like a real life game scenario of soccer. And we described the game in terms of the three things that we need to describe the game. We needed the players, the actions, the payoffs. Players being attacker and goalie, actions being left or right, and payoffs where these 1 and minus 1 win or lose. Very simple payoffs. What game theory promised us is that it would give us predictions for every scenario of what we should expect to see. And we were trying to hold game theory to its promise. So what we did as the first step was, not even in this slide, this was our first slide when we started working on this. And what we did is we first calculated the best responses for each game. And when we calculated the best responses, it turns out that there was no cell where a triangle and a square coincided, which told us that that method wasn't giving Nash equilibrium out of this game. And that led us to looking for something beyond that method. And we said that the way you would get a solution to it is by being unpredictable. There is a name for this unpredictable Nash equilibria. We call them, I use quotes because unpredictability is just something that's intuitive that I'm calling it. The name for this kind of Nash equilibrium is mixed strategy Nash equilibrium. Let me now tell you what it means. This is the name for this. Okay, no space to finish equilibrium. Mixed strategy means people are mixing among their actions. Mixing means they're putting things together. Okay? So randomizing or mixing between their actions, that's why this form of a Nash equilibrium is called mixed strategy Nash equilibrium. We start by assuming that both players are going to mix among their actions. They're going to try and be unpredictable. We don't know how exactly they want to be unpredictable. That is going to be determined by the parameters of the problem. So we start by putting in placeholders. We say that suppose these unpredictable strategies that are going to be played, that's step 1, is P1 minus P for the goalie and Q1 minus Q for the other. Suppose. That's step 1. Step 2 would be that use the idea that the fact that these guys are randomizing, the fact that they're mixing among their actions, the fact that instead of choosing the same action all the time, sometimes they're choosing this and sometimes that, they can only be doing this if somehow these actions are giving equal payoffs. And as I told you, you can think of the short choice for interview example that I gave during the class, if you ever are in doubt. The idea was that if I have multiple shirts and I have these important interviews to attend, I should be wearing my best shirt to all of these interviews. Clean it, iron it, wear the same best shirt, if I have a best shirt. If I'm randomly choosing among my shirts, it must be that I think all of those shirts are equally good. All of those shirts would make me look equally presentable at my interviews. Similarly, if people are mixing among their actions, picking this action sometimes and that action sometimes randomly, it must be that all of these actions are equally favorable to them. They must be getting equal payoffs from them. There must be indifference among them. So that was step 2. That was a step of reasoning. Step 3 is take that step of reasoning and apply it mathematically. So think about the payoffs that any player would get from each of their actions, and then use indifference. Indifference means those payoffs must be equal, and then solve for P and Q, the placeholders that we have. And then that gives you a P and a Q so that each player is maximizing their utility because they are indifferent, so they can maximize their utility by mixing. And that ends up giving you this P and Q and this final equilibrium. Why is this an equilibrium? Because as long as the goalie plays this strategy and the attacker plays this strategy, no one has a reason to deviate because they are both doing the best that they can. There's nothing else that would give them a strictly higher payoff. It's also a prediction. It is telling you that you actually have a game of soccer where the payoffs were exactly that. And if you watch the game many times, then over those multiple occasions, you would see that the attacker and the goalie would go left and right roughly equally, 50-50 times. That's what the prediction of this game is. Okay? I could have made the game slightly more complicated where I could have put in more actions and I would have to then think about what those payoffs are. But as long as you give me actions and as long as you give me payoffs, I can always get a Nash equilibrium prediction. And then I can go out to reality, collect data from actual games and match them and see if the predictions actually predict real life. And this is something that people have done. So there are papers where what they looked at is, they looked at these penalties taken by a big player like Messi or Ronaldo, and not just these two players, but let's say all of the players from the Champions League and the World Cups. So they would look at penalty patterns of how often do players kick left and right, and they would also look at the goalies' diving patterns, how often do the goalies go left and right. And game theory gives you a prediction, and then you can see if the data matches the prediction. And it turns out the data matches the prediction quite well. And people have not just done it for soccer, they have also done it for tennis. So for tennis, think of it as, there's many ways to think of it, but maybe it's Roger Federer versus Nadal 10 years ago. We're back. So you could look at a Nadal versus Federer game, but not just any Nadal versus Federer game. You could look at all of the ATP circuits and the Grand Slams together. You could collect the data, and then you could think about a similar game where players are thinking about whether to return to the guy's forehand or backhand, or whether to return to the half courts, the left or the right half court. And then once you write down the game, it would give you a prediction of over multiple repetitions of the game, how frequently should you see each action being played. That would give you a prediction. And then you have this data because we have video recordings. So you can just look at the data. And then you can match if these predictions match the actions. And it turns out again, even in those scenarios, game theory does predict it very well. Because you have high quality players who are really trying to best respond to each other. Right? And you would think that that should give rise to something like an equilibrium. And given the equilibrium is something like this, it says that, it tells you exactly the proportion of times people should be doing certain actions. It's a perfect prediction you can test. So that's how game theory is also useful when thinking about sports and sports related data. Okay. So with that, now we are going to go to the next topic. The next topic is going to be something that's really interesting, partly because it's super surprising that it turns out to be that way, which is the topic of oligopoly. There are slides on it. but we don't need to go to the slides. I can just tell you what is important for the oligopoly problem on the exam. So here is the topic of oligopoly. Monopoly means there's just one firm in the market. Oligopoly means multiple firms in the market. Okay, so this just means multiple firms. And if you remember when we started talking about game theory, we said that one of the reasons we want to study game theory is because we want to understand how do firms compete when there's multiple firms. We studied perfectly competitive markets, which was this case where there's infinite number of firms. So all that competition boils down just to the simple fact that you are a price taker. And then we studied the other extreme where there's just one firm. So you're a monopoly, you don't worry about competition at all because by definition there's no one else. But what happens if there's two firms or three firms? How should we think about how would firms behave in those cases? And that's the topic of oligopoly, multiple firms. It turns out there are two ways in which economists had thought about this problem. There were these two mathematicians in the 19th century. So there was Cournot. They were both French. So Cournot came up with a theory in 1838, and then Bertrand came up with another theory in 1883. They were both trying to address the same question, but they came up with slightly different answers because they assumed a couple of slightly different things. So Cournot assumed that firms compete by setting quantity, and this is why he gave a theory for quantity competition. And Bertrand, let's separate it here, instead said that I'm going to assume that firms compete by setting prices. Not by setting quantities, but by deciding what prices at which they're going to sell stuff. And that gave rise to this idea of price competition. So they were giving different theories, and the theories mostly differed because they had different assumptions of how firms compete. Now the reason I teach this, or people generally teach this after game theory, is because if you think about Nash's idea and Nash equilibrium, I'm going to use a different ink, it's because this is a slightly different topic. Nash was writing in the 1940s and 50s. What is super surprising, and this is probably the most interesting part of this for me, is that Cournot and Bertrand, even though they were writing more than 100 years before Nash, they actually came up with ideas that were very similar to Nash's theory. So whatever I'm going to show you right now is going to really resonate with Nash's theory and whatever we have learned so far. Okay? So what that means is, if you think about the way we think about Nash equilibrium, so there are players, think of the thing that we always do. There are actions, there's payoffs, right? That's what defines a game. And then there are best responses for each player, and a best response from each player taken together, like when all players best respond, it gives you an equilibrium. This idea is also going to be reflected in Cournot and Bertrand's idea of how to think about firm competition. So they somehow managed to think of things very similar to Nash, even though they were way ahead of him. So it's quite likely that Nash might have derived some of his ideas from reading the book. So how do we think about this? So let me take a particular question from Cournot and Bertrand. So let's use this question. This is from homework 5. So think about this question. There's two firms, Wings and Wingstop. They're going to compete among each other, which means with two firms, the theory of monopoly doesn't apply anymore. The theory of perfect competitive markets doesn't apply anymore. These are both chicken chicken wing places, so they're going to sell chicken wings. They're going to sell slightly different stuff. You can solve it assuming they are doing quantity competition, or you can solve it assuming they're doing price competition. We can do both. Let's start with one of them. Let's start with the quantity competition case. What is given on the question is the demands that are faced by each firm, and I'm going to write that down first. So it says that we are in an example, so let's call it an example. So this is the example of Kuno we are going to study. And the example says that there are two firms, so Firewings and Wingstop. They're going to have different demands. The demand for Firewings would be PF and the demand for Wingstop would be PW. Firewings demand is 112 minus QF minus 0.5 QW, so 112 minus QF minus 0.5 QW. It's easier if it's 0.5. And then for Wingstop, let me just write it down. This is how the demand curves look like. Okay? What is different than before in monopoly was that in monopoly, your demand curve was the price you face is a constant minus the quantity you produce without this term. Because you're a monopoly. Your price only depends on how much you produce. But now, there's another guy in the market. So the price you can charge depends on not just what you produce, but also what the other guy produces. QW, the other guy's quantity. So what it means is, if the other guy raises their quantity, it's also going to lower your prices. Because some people are going to buy it from them, so that, right? You can't have that high prices anymore in the market. The supply has gone up. The supply is determined by both you and the other guy. The other guy can increase their supply, that's going to affect your prices. And similarly for the other guy. When you think about Wingstop, the price they can charge depends on how much they produce, how much they supply, but also how much the other guy supplies. Because the total supply now comes from both of the firms. So that's what gives you equations like these. And that's clearly different from what we have seen so far, to some extent. This is clearly a game because these are strategic interactions. Now, the outcome from my decision doesn't just depend on what I do, but also depends on what the other guy does. And that's what makes it a game. Now think about how we always think of a game. For a game, we need to have players. It's clear who the players are. It's Firewings and Wingstop. We need to have actions. And given this is Kuno's world, and Kuno says the firms compete on quantity, the actions have to be the quantity that these firms produce. So the actions need to be QF and QW. Okay? And then it comes to payoffs. What is different from the game theory problems we have done before is that I haven't given you a table where the payoffs are given, but the payoffs are simply going to be profits. The profits of the firms, pi f and pi w. And as long as I can calculate pi f and pi w, I can say this is a game and I can solve it the same way as I've solved every game. So what does that mean? Let's think about it. Let's think about pi f to begin with. What is pi f? This is profit for Firewings. Firewings? Firewings is the name. Okay, so profit is, as always, revenue minus cost. What is revenue? Revenue is price times quantity. So it must be the price that Firewings charges times the quantity they produce minus the marginal cost. What is given on the question, let me write it down in a different ink. The question says that the marginal cost for both of the firms is 5. So I'm going to use that information. So what that tells me is marginal cost is 5, and then the amount they produce is QF, which tells me that is the total cost. Let me pause there. Is that clear? Profit is revenue minus cost. Very good. So then what I can say next is that, look, this PF is already given on the question. So this is going to be 112 minus QF minus 0.5 QW times QF minus 5 times QF. So this is the profit. So even though I haven't given you the profit in a table, I can clearly calculate the profit. This is the profit. Just revenue minus cost, as always. The next order of business would be to calculate a best response. What is a best response? Generally, best response means for QW, which is my opponent's action. What is my best action? That's the question of best response, right? And given this is quantity competition, my action has to be, my action is QF. I just need to find out the best QF for me, the best action for myself. So how do I maximize this pi f with respect to QF? How do I figure out the best QF for me? What should be the trick I use? Just the derivative, like we always did for monopolies. So what you would do is, you would take the profit of this firm, you would derive it with respect to the quantity. Remember, the quantity derive with respect to quantity because this is quantity competition. Which is also called Cournot, as we saw on the last slide, and forms strategy is quantity. So you need to take the derivative and set it equal to 0 as we always do. And if you do that, the derivative is going to give you, I'm just going to write it down, you can check it later. It's going to be 112 minus QF minus 0.5 QW minus QF minus 5 is equal to 0. That is going to be, this thing right here is F's best response. So phi wing's best response is that equation. It's an equation. You could also think about Wingstop's best response. How would you do it? Let's use a different ink. No, so let's do the same. Now for Wingstop. How would we do it? We would first figure out Wingstop's profit. Profit is, as always, revenue minus cost. Revenue is Wingstop's price times Wingstop's quantity minus 5 times the quantity produced. The price is given. I'm just going to write it down from here. It's 130 minus QW minus 0.5 QF. So 130 minus QW minus 0.5 QF. There's QW here. There's the 5. That gives me this equation. That's just revenue minus cost. Revenue is price times quantity. Nothing else. What should be the next step? I should be maximizing my profit with respect to my quantity. So I need to take a derivative and set it equal to 0. And if I do that, what am I going to get? I'm going to get the following. It's 130 minus PW minus 0.5 QF minus QW minus 5 is equal to 0. What I write down as the derivative, you could always calculate it yourself. It's just a derivative. You've taken the derivative many times. Okay, that gives you a best response. So what did we get at the end of this exercise? We got two best responses. Let me pinch it so that it's small. What are the two best responses? Maybe I can put a box around them. So here is the first best response. Firewing's best response is here. And here is Wingstop's best response. These two equations with boxes around them. For a Nash equilibrium, both forms must best respond, which means that both of those equations must hold. So what should be the next step to ensure that we find values such that both equations hold? How would we do it? Okay, that's the most popular answer that I always get every year, and that's wrong. So you don't want to equate the equations, you want to solve for those two equations. Because if you solve for them, what you get is values where both these equations hold. That's the solution of equations. So let me just write it down. So let's say that this equation, I'm going to call it equation 1. And this equation at the very end, I'm going to call it equation 2. What you want to do is solve 1 and 2. If you solve 1 and 2, what are the unknowns in this equation? QW and QF. And that would tell you in equilibrium how much quantity should Wingstop and Firewings produce. QW and QF. And that is Couno's idea of how forms would compete among each other. Each form would try to best respond to the other form. That's going to look like an equation like this and an equation like that. And now that you have these two equations, you can solve for them and it would tell you what's the value of QW and QF where both forms end up best responding to each other. You have it kind of.
So are you doing a system of equations?
It's just a set of two equations, right? How do you solve for two equations like this? What would be the trick? Substitution. You just substitute one into the other, find a variable, substitute it in the other, and then you're done. So that's just quantity competition. Now let me just say one last thing. We have 5 minutes. How would price competition be different? The main difference between Couno and Bertrand was the following. Bertrand said that the players in this problem are still Firewings and Wingstop, but the actions, because Bertrand was talking about price competition, the actions would be the prices they set. So PF and PW. The payoffs are just the same as always. It's going to be the profits that these firms get. So the only thing that really changes from Couno to Bertrand is the fact that the actions that the firms want to take, instead of setting quantities, here firms are going to set prices. So how are we going to do this? What is going to change? The only thing that is going to change is that when you want to find profits, so you want to find phi F and phi W, not in terms of QF and QW, but the prices. You want to find the profits in terms of prices. That's going to be one difference. And then the second difference is when you take the derivative, you don't take the derivative with respect to quantity anymore. To find best response, you take the derivative with respect to prices. Okay? So the main difference between Couno and Bertrand is because this is quantity competition, derivatives are with respect to quantity. Because every form is trying to maximize profits with respect to quantity. But when it comes to Bertrand or price competition, every form is trying to maximize profits with respect to prices instead. So when they try and maximize profit, their best response is they're going to take this derivative with respect to prices and not quantities. And that's the main difference. That's the only difference. The steps are all the same. You would calculate profits, which is always revenue minus cost, and then you would take derivatives with respect to prices, and then you would solve for the two equations that you get. And that's it. Okay? Any questions about the steps? Okay, so then we are done with this class. And then I'll see you folks on Tuesday, which is the midterm day. I'm going to have office hours on Monday for sure, and maybe also on Friday, which will be extra office hours. I'll send an email about it.